In this video, let's practice on solving regular motion problems. Here's a scenario. An airplane is flying with an air velocity of 220 meters per second towards east. And there's also wind. And the wind velocity relative to the ground is 50 meters per second. And now our job is to figure out the velocity of the airplane relative to the ground. Okay, before we jump into the math, let's break down exactly what these terms mean. First, we have the air velocity. What does that mean? The plane's air velocity is not the speed relative to the ground. Okay, it's the velocity relative to the air. Think of it like this. Imagine the air around the plane is a giant invisible bubble, and the plane is flying inside this air bubble. Now let's add the plane, and this plane is moving at 220 meters per second inside this air bubble, as if the air bubble were perfectly still. We can express this velocity as VPA is the velocity of the plane versus the air. Okay, this is exactly the same idea as when you are walking on a moving train. See, this is the train. Your velocity, say 1.2 meters per second, is measured relative to the train itself, not the ground outside. Okay, so in this problem, the air is acting just like the train. Now, in reality, our air bubble is not standing still, it's also moving. And that moving air is what we call wind. So the wind's velocity is simply how fast this entire air bubble is moving relative to the earth or to the ground. And we can express this as VAG. So it's the velocity of the air relative to the ground. And the question tells us that the wind speed is 50 meters per second towards north. And this is analogous to the train with a certain speed relative to the ground. In that case, both you and train are in motion. Similarly, in this airplane case, both the airplane and the air are in motion. What we are solving for is the velocity of the plane relative to the ground. So we can write it as V plane to the ground, VPG. So mathematically, VPG is an addition of two vectors. VPG is a vector. It's the addition of two vectors, the air velocity, VPA, plus the wind velocity, VAG. You might be wondering, how can you be sure this is the right way to set it up? A simple way is to look at the subscripts. See, the A for air is a common subscript. When you line up the vectors like this, the common A essentially cancels out, leaving this P and G for plane relative to the ground. Generally, this is the rule for any relative motion problem. If you know the velocity of object A relative to object B, VAB, and you also know the velocity of B relative to a third object, C, VBC, then you can always find the velocity of A relative to C. So you can get VAC by adding these two vectors together. See how B is in the subscript of these two vectors, which represents the intermediate object, and it cancels out when you are adding these two vectors. Okay? It's a neat trick for setting up your equations correctly every time for the relative motion. As you can see, this equation is addition of two vectors. We can't simply add the numbers together. So let's draw this out to see what it looks like, and then we turn this into something that we can solve algebraically. Now, we know that the air velocity, VPA, is a vector pointing east with a length representing 220 meters per second. To add the wind velocity, we'll draw a new arrow starting from the very tip of our first vector and has a length representing 50 meters per second. So this is VAG. Now VPG is the result of adding these two vectors together. We find it by drawing this vector from the very start of the first arrow to the very tip of the second arrow. So this is VPG, representing the velocity of the plane relative to the ground. As you can see from our drawing, these vectors form a right-angled triangle. This is perfect because it allows us to use the Pythagorean theorem to find the magnitude of this final vector, VPG. So algebraically, we can find the magnitude of VPG by using the formula VPG squared equals to VPA squared plus VAG squared. Now we just need to take the square root of both sides to get our final velocity. VPG is square root VPA squared plus VAG squared. Now we have turned this vector equation to a solvable algebraic equation. Now let's plug in the values into this equation. Then VPG equals to square root of VPA is 220 meters per second squared plus VAG is the wind velocity, so it's 50 meters per second, then squared. This gives us a speed about 225.6 meters per second. And this is the speed for the plane relative to the ground. That's a little bit faster than its air velocity, right? Which makes sense because the wind is also pushing it along. Let's find the direction of this velocity vector. Let's say we want to find this angle, theta. We can use any primary trigonometry function to solve for it. The easiest one to use here is the tangent function because we know the lengths of both opposite and adjacent sides of our triangle from the problem. Let's set up the equation like this. So tangent theta equals to the opposite, which is VAG, then divided by the adjacent, which is VPA. Now we can plug in the values. It equals to 50 meters per second for VAG, divided by the VPA is 220 meters per second. So it equals to 0.227. To find the angle theta, we'll take the inverse tangent of 0.227. So theta equals to 12.8 degrees. So the velocity of the airplane relative to the ground is 255.6 meters per second and an angle of 12.8 degrees from east to north.